Engineering Product Manager and the Body Development Department R&D Manager at IDIADA. His current responsibilities are related to business development of the aerodynamics and CFD services within IDIADA. Mr. Aramburu has been working in the automotive industry for more than 25 years, and during that time, he has been involved with more than 50 vehicle development programs across a variety of automotive OEMs. And he's here today to speak to us about the Upscale project.
Thank you, Enric.
I will hand over the control.
Thanks, the PPC organization, for inviting us. I'm presenting today on behalf of the Upscale consortium. So, yeah, let's go ahead with this. Let's see if my computer, okay, here we are. Well, the Upscale project is a project about using artificial intelligence and machine learning for CAE simulation in the context of finite element, finite volume, 3D simulation. I used to say that the Upscale project is born from a necessity and from a opportunity. From a necessity, we realized that with new energy vehicles, with new energy vehicles and electric vehicles, we need new simulation tools, we need new applications that requires simulation in several orders of magnitude of more speed than what we have today. For instance, when we want to simulate a crash of a complete vehicle, including a complete battery package, which means we have maybe hundreds of battery cells, and a single battery cell is really complex. And in the end, we want to assess a shortcut or the probability of a shortcut in any of these battery cells. Can we do this with the current CAE tools? The answer is not. Well, maybe we can do with simulation that could last months, let's say. Okay, so currently this is not feasible. So clearly there are some new design analysis that needs breakthrough technology to do so. Basically, what we realize is that Enric was mentioning, and personally, I'm in this industry since maybe more than 25 years. And what we realize is that the development of these CAE tools has been really very incremental. So we have been improving little by little, but we are using the very same tools in the last 10 years or 20 years or even more. So the finite element approach, the finite volume approach is more or less the same. That's been improved, really. It's been made much more complex, really, but in a very incremental way. Thanks to the Moore law, for instance, where we have much more powerful computers. But what we need now is something different. It's a breakthrough that increases the performance of the CAE tools by orders of magnitude, not in such an incremental way. An example was this crash with full electric vehicle, or maybe aerodynamics, or maybe thermal runaway. So we have these kind of challenges that needs new solutions. And that's the necessity. And the opportunity, what's opportunity? The opportunity is clearly artificial intelligence. Artificial intelligence and machine learning. However, this is a completely change of paradigm. So what does it mean using machine learning instead of finite element, for instance? So in finite element, what we do is solving the physical laws through our domain. We find out what are the physical laws that are governing the domain, and then we find out a numerical method to solve the equations derived from this. This means sometimes long simulation times to solve these systems of equations, which used to be very complex, etc. However, this is a very robust process. Well, what we are proposing with machine learning is something completely different. It's something that's learning from data. So if we have enough data that represent the situation that we want to study, then we apply machine learning tools to extract some patterns that reproduce the same behavior of this problem. However, this could be a bit blind, okay? And something that's really frightening to engineers is that we are going away from the physical laws, okay? So it's really a good opportunity, and it's really a big risk. However, we deemed it was worth to try. Let me say that this is a very hot topic. 5 years ago, nobody, I think, was speaking about this. And right now, besides Upscale, there are several other initiatives. For instance, in the aeronautic sector, there is a project trying to do similar approaches, or software vendors are trying to apply artificial intelligence and machine learning to solve some of unresolved problems. That's the approach. Okay. So in this project and through this presentation, we are going to comment on these applications, on first results that we are already achieving through the project, and the key thing is whether the effort that's needed to generate the data is worth, and what's the accuracy that we can achieve, and how we can manage this accuracy. Because right now, as I was telling you, solving the physical laws is a very robust process. So once you are checked that you are doing well, the process is correlated and you can trust this. In the case of artificial intelligence, whenever you change the data that you're using to train the model, the accuracy could change completely. So that's why we are saying this statement, garbage in, garbage out. This depends very much on the data that you are using and in the process that we are using to manage this data. So this is a summary, this is like a summary of the objectives of the project. As was mentioned by Alain, in this call, we were supposed to achieve 20% of acceleration in the development process. And what we are saying in the Upscale project is that we are achieving this 20% by accelerating the simulation processes by orders of magnitude. Well, who we are, this is the consortium of the Upscale project. You can clearly identify here several OEMs that they are working as end users or testers, not only end user of testers, they are only developing the methodology that we are showing next. We have SME entities, we have consultants or experts in the field of machine learning and artificial intelligence, we have research centers, and we have software vendors that they are finally applying and exploiting these solutions for the general public. This slide is more about the final applications that we are addressing. Some of them are highlighted. For instance, the first topic, aerodynamics. Well, we identified two main blocks, CFD and crash here. And in the field of CFD, first main topic is aerodynamics. So what we want here is to generate aerodynamic surrogate solutions, surrogate models. So are we able to compute the aerodynamic coefficients directly just looking at the geometry of a new car? So this is the challenge. Or other topics that instead of surrogating completely the simulation, we are just improving some pieces, some parts of the simulation process. Some of these are listed here. The data-driven turbulence modeling, where we are improving the turbulence modeling. New improvements that are implemented also in CFD solvers. And in the block of crash, very clearly we identify the reduced order models for battery. But not only this, we are also developing new contact algorithms accelerated by machine learning, new partitioning strategies for parallel simulations based on machine learning as well. So many different applications under the umbrella of the machine learning technology. Well, this is the structure of the project. Basically, we identified two pillars, as mentioned before, crash and CFD. However, in the first work package, we assumed that we could work in some techniques that could be exchanged, that could be useful for both outcomes, for aerodynamics and crash. And then we separated to both to all these two pillars. So in work package 2, we are developing this new framework for aerodynamics and CFD. Work package 3, this new framework for crash. And then finally, work package 4 and work package 5, we are applying to real industrial cases. Currently, we are in month 24. So more or less, we have developed this framework that's already implemented, that's taking advantage of machine learning to do these new simulations. And in the next months, we will be applying to the demonstrator to the real cases. So let's start with the first topic. Our goal in this case for aerodynamic artificial intelligence surrogate models is having a real-time aerodynamic simulation. This means, what if we are working with a designer, the designer is modifying the shape of the vehicle in an interactive way, and then what if we are able to provide the impact of these modifications instantly on the aerodynamic forces? That's the challenge, okay? So we realize that we can do this, and we can do this by parameterizing the vehicle. So if we are able to parameterize the shape of the vehicle, and we know when we are modifying this vehicle, what are the parameters that are changing, and we can find the dependency of the aerodynamic forces on these parameters, we will achieve the goal. We'll be able to get the aerodynamic forces instantaneously. So we figured out two ways of doing so. First, and more intuitively, is by parameterizing the typical geometrical conditions of the vehicle shape, okay? For instance, if we have a parameter that's considering the distance of the vehicle to the ground, or whether we have a parameter that's modeling a distance, the complete length of the vehicle. So geometrical parameters that in the end define a new shape. Whether then we can modify these parameters, we modify the shape. We are showing here the result of this in 3D, but basically what we are showing today and the results that we are showing today have been obtained with the first trial with 2D studies of the aerodynamics of the vehicle. So in this case, in 2D, we are assuming that the vehicle can be parameterized with 17 parameters, and then we can morph the vehicle, we can modify very easily by modifying this. Then in this case, we generate the data. We need this data, the aerodynamic forces. We generate the data by doing CFD simulation of all the variations of all these 17 parameters, which could end up, for instance, with something close to 1,000 simulations. So if we are running all these cases, then we fit our machine learning tool, we fit our regressor with this in order to achieve to get the aerodynamic forces. However, this has a limitation that we can only identify the shape of a vehicle by modifying these parameters. But what if the vehicle has been modified in a different way and we get a new shape and we want to also compute the CD, the aerodynamic forces for this. So then we are applying a different approach. That's what we call the universal parameterization. To do so, we use an autoencoder, encoder-decoder approach. This is based on level sets, and this is very similar to what's being used, for instance, for image recognition or for face recognition. Okay, so yeah. But the basic idea is that your in this case 2D two-dimension section is defined by what's solid, what's fluid. So if we are identifying this in an array of pixels, in this case, this is our level set. There are techniques, these are encoder-decoder techniques that are able to reduce this, let's say, pixel map to a minimum number of parameters. This is a mathematical operation, and then to reduce this, for instance, from this array of 256 by 256 to 10 parameters, and from these 10 parameters, you can then regenerate the same shape or the same description. So this is our idea for our universal parameterization. So if we are able to parameterize any shape in this way, either the physical, either the mathematical, let's say, and we have all these data, so the aerodynamic forces, we can use different regressors. We are just showing here a long list of regressors that we are trying. So we are now in this point with all this framework is in place, and we are trying with many different regressors or machine learning techniques, and playing with the different options that we have for all this, okay, in order to find out what's the best solution. We are providing here a table with all the error that we are achieving for this. So the strategy to do so basically is, okay, we have all this long list of results, the aerodynamic forces, and we use, for instance, 75% of this to train, and we keep 25% of these values to check whether the accuracy is good or not. So we are using 25 random cases, 25%. We compute the aerodynamic force and we compare with the one that it's assumed to be the real one. By doing so, we can check the error. This is the same approach that we are using in the project for any machine learning application. So what we can see here first is that with some regressors, with some of these machine learning techniques, the physical parameterization and the autoencoder works in a similar way, with errors around 5% for the average error. Let me say that we have a target of 2% here, but with the autoencoder, we're struggling to improve this. However, with the physical parameterization, and in this case, with this machine learning kriging method, we are achieving very good results. We are below 1% in average error for these testing cases. So this is very good result, very encouraging. And currently, we are working to improve for the autoencoder as well, to reach this by trying different parameters, trying different ways for the autoencoder, etc. So we are now working, we have everything installed, and it's very easy to try very different strategies. But what if we don't want only to simulate the aerodynamic forces and get these aerodynamic forces in real instance, in matter of seconds, but also as designers and aerodynamicists, we want also to look at the airflow to understand why we are achieving these forces and not the others. So what we are showing here is that there are also other techniques, also based on this level set, to reproduce the flow maps, okay, the velocity, etc. So this is an ongoing process that's also being developed in this project, and currently we are using convolutional neural networks to reproduce these velocity maps, pressure maps in different in a level set of around the vehicle and in the surfaces of the vehicle. So this is for the artificial intelligence surrogate aerodynamic models. However, and then we are trying a second approach, completely different approach. Instead of getting a completely new solver, predictor, let's say, of the aerodynamic forces, in this case, we are taking advantage of artificial intelligence to improve our current solvers. Basically, the idea here is, okay, in CFD, we are using range models, which are quite simplified, are steady state. We are averaging the main variables as pressure and velocity. And we know that by doing so, we are introducing in the equations, in the momentum conservation equations, an error that basically is coming from computing a new source term that appears in the equations, that it is the what's so far called the Reynolds stresses. Okay, so our idea is that these Reynolds stresses depends on several flow parameters. So we take high fidelity solutions, high fidelity simulations like direct numerical simulation results or robotic methods. We take, we look at these variables in the high fidelity, and we look for the dependency of the Reynolds stresses, which are changing completely the flow field, if we are computing well or not, and we try to get the Reynolds stresses dependencies on the flow field variables. That's what we are implementing as well. To do so, well, what we are showing here is what we are using to train these, okay? So these Reynolds stresses field in the case of direct numerical simulation, so high fidelity of, in this case, this airfoil, you can see looks completely different to those in the simplified model, in the range model. Well, then what we are doing is different DNS simulations, different range simulation, and we look at the variables of, I don't know, gradients of speeds, for instance, kinetic and turbulent energy. So many different parameters, up to 10 we are gathering, and we look for these dependencies. In this case, what we are showing is that so this is a universal solver. So we are using different flow cases to train a solver, and the solver is not dependent on the case finally. So we are, in this case, using 2D cases, this airfoil, this backwards facing step, etc., at different Reynolds numbers, and then we want to check with a different simulation case. That's what we are showing here. So in this case, we try it with the backwards facing step, which we assume more challenging to compute the Reynolds stresses and the turbulence. And what we see is that the RAN solution, so the simplified case, the Reynolds stresses are completely different to the real ones, which are computed by direct numeric simulation. And then we are applying this technique to correct the upper left picture, let's say, the Reynolds stresses, to correct this flow field based on a machine learning algorithm. And what we are trying here also is to correct, in this case, for a different Reynolds number compared to the training cases. So the result has been very successful. Now everything is in place, this framework is ready. And well, we are now in the moment where we are trying many different strategies, not only correcting the Reynolds stresses as we are doing now, but computing directly the Reynolds stresses and integrating this through the solver evolution. So many different strategies can be tried now, and it's really exciting time for this development. Well, let's change completely the topic. let's go to the crash, one of the crash applications. As mentioned it before, we are not only developing these battery reduced order models, but other algorithms that are taking advantage of machine learning to improve our CA process. But this is really very good example of how we can take advantage of machine learning. So as I was mentioning before, it's impossible to simulate a battery pack, full battery pack, including all the battery cells by CAE, by finite element modeling. Only one cell could mean more than 4 million finite elements, because this is really complex. You have a lot of layers, different materials, really thin layers, etc. So what we want to try is, okay, we have one of these very detailed cells, and we deform this with many different load cases that are similar to the load cases or to the forces, to the displacements that that will be applied in a real crash over one of these cells, and then we want to get a machine learning model that behaves in a similar way to this one. The good thing is that the reduced order model will run in several orders of magnitude quicker than the real case. So that's the goal. To do so, we have also utilized, this very detailed model is what we call a meso model. We have utilized also what we call a macro model. So it's not a reduced order model, but it's a simplified finite element model that behaves in a similar way to the real detailed one. And very important to mention that we are not only looking for the structural behavior of this cell, we are looking also at the probability of shortcut. So in this very detailed cell, we are always assessing whether the internal membranes are broken and the electrodes are touching. In the finite element, we study this, and then the results from this are used to create the reduced order models to mimic the behavior of the cell and to reproduce the shortcut probability. So by doing crash tests, we derive so up to 27 load cases that are are reproducing all the scenarios that the cell could face. These 27 are divided in 3 kinds of cases: bending, three-point indentation, spherical indentation, and at different positions of these tests. And then we generate lots of data of all these cases at the different time states. So with all this information, what we will generate is our reduced order model. So what is this reduced order model? A reduced order model is something that, in this case, substitute all that's inside the cell. So our new cell will be just the envelope, and everything that's inside the envelope is our reduced order model. So this means that in the finite element, we are simulating the complete, all the layers, etc. And we are getting the reaction forces of everything that's inside the envelope. So the reaction forces are the result of our reduced order model. So whenever we will run later the reduced order model, the envelope, when we apply a deformation on the envelope, the reduced order model will provide a reaction of the node that's touching with this envelope. So in the end, we'll behave in the very same way, and the deformation will be exactly the same, but in several orders of magnitude quicker than what we are doing in the finite element. So that's the approach. And then on top of that, we are also, as mentioning before, computing the probability of shortcut. Okay, so that's the final result of the shortcut. Basically, the shortcut is computed, I would say, in 3 steps. First is the computation of the deformation, of the strains, of the stresses, etc. Second step is for this deformation, we classify the behavior of the cell in whether this is similar to 3-point bending, similar to cylindrical indentations, similar to spherical indentation. And when is this classified, we have a specific model for shortcut for any of these. What we are showing here is that we are trying different regressors for any of these 3 cases and the result. So finally, what we find out is the accuracy of this probability of assessing the shortcut falls in the range around 5% error, which is really good. So this is something that we couldn't do in the past. Now with this approach, we are able to say with 95% of probability that our shortcut is identified or not. So this is really a useful result for our engineers. So this is a short explanation of some of the outcomes of the project. And last slide in my presentation is an insight for this crash about the acceleration that we get. So these are some simulation times that we are realizing here. So just for you to show, the finite element of a single cell could last 15 hours with 128 cores, and the reduced order model goes below 23 seconds with 12 CPUs. So we are improving this by 6 orders of magnitude. And then on top of that, we compute also the probability of shortcut, then it's much more even quicker, so it doesn't really increase the simulation time. So finally, we can demonstrate the advantage of using this. So yeah, here it comes to the end of my presentation. What we have been showing is that these techniques in these 24 months are being implemented, and now we are trying different strategies, and finally we'll be applying to real cases. And the final goal of the project will be this implementation, but also assessing the feasibility of using this in the real world. So trustworthiness is really important and really depends on, it's really data dependent and machine learning method dependent. So we'll have to reach our conclusions whether this is acceptable or not, and also whether it's worth, in the case that we need to generate a lot of data upfront or let's say offline for a very fast simulation, but if the effort that we are doing upfront is too big, maybe it's not worth. So all these kind of conclusions is what we want also to get and define at the end of the process. So thank you very much. And that's all from my side. If you have questions, I'll try to answer now or maybe in the discussion panel.
Okay, excellent. Thank you. And as always, it's a little awkward on these Zoom calls. I'm sure everyone's applauding privately in their individual offices. And I want to remind everyone to send questions through the Q&A button, and remind you as well to put in your affiliation so I can read that out as you have questions. And I guess I can start with a question from Dr. Busquerol here, which I think is an interesting one to start with. That is that could we imagine replacing some crash tests batteries with simulations of crash testing, and just to what degree could simulation replace a lot of rather expensive and time-consuming real-life physical testing, and how might those two be integrated?
Yes, the answer currently is yes, that this is what we are currently doing. The idea is also, well, these reduced order models of cells, we can figure out that we can also try with other components as well. And the key thing is always, well, it needs a lot of effort to generate data to train, and whether this is worth. So If you need the equivalent, let's say, for instance, to 100 simulations of the cell, if you are not doing more than 100 simulations later on, this doesn't make sense. So this is the kind of things that we need to assess. And then again, the trustworthiness is not dependent on the physics now. It's dependent on the information that you have put inside. So that's the key question, whether to use it or not. But in this case, for instance, where now it's not possible by, let's say, traditional CAE or finite element, there is no choice. So it's whether we use this maybe or we skip this. And usually in this case, what we are doing is over-dimensioning the battery packs, etc., because we don't have the design tools to do so. So yeah, the answer is yes. This is something that we are currently doing, and this can be extended to other parts of the vehicle, can be simulated in this way.
Okay. Yeah. I have another good question here that's probably on the minds of many in the audience from Eduard Reclaro, and that is, can these models be easily built by application engineers that are not specialists in machine learning, or does it require a reasonable amount of advanced knowledge in machine learning algorithms?
Our experience is that this is easy to do. It's easy to replicate. There are many different toolkits for machine learning applications. So if you have your data, if you're able to clean the data and provide the data in the proper way, so it could be even kind of Excel sheet with all the columns with all the data, you can have all this, okay? And there are many toolkits where you can do this easily. However, it's good to have experience in the methods, okay? Because it's really providing more efficient ways to doing so. So which is the most appropriate method? Which are the parameters that we should use? What's the better way to validate the accuracy? All this is provided by these machine learning experts. So the tools are easy to get, accessible, but everybody can use it, I think. And then the point is to know how to use it.
Okay, great. One more question. I'm going to use my prerogative as the chairman to ask my own question really quickly. And that is, you described how these tools have been used to assess different designs, with the vehicle, the fluid dynamics flow. But arguably, once you have these tools developed, you could let the artificial intelligence essentially do some of the design work of the vehicle if you gave it certain constraints. And I'm sure that's kind of a future thing, but to what degree have you considered using the validated tools and let an artificial intelligence do some parts of the design work?
Unfortunately, I couldn't cover all the outcomes of the project. This is also one of the outcomes of the project. So the next step is using this in the frame of an optimization algorithm. Okay. So then that this optimization algorithm is providing you the best result of the best performing parameters of that are defining this vehicle shape. Yeah, this is included as one of the final outcomes of the project.
Oh, excellent, interesting. Okay, for the sake of time, we should probably press on. So I'd like to thank our second speaker, Enric Aramburu.
Thanks to you. Time. I'm sorry to extend it a bit more.
It's okay. It's all interesting stuff. So I'm hopefully the audience is enjoying these presentations as much as I am.